computer.
Okay, we're finding segment lengths in circles. Be really careful that what we're learning today doesn't get confused with what we did last time. So for example, this looks very similar to what we learned last time with angles inside the circle that are formed by two chords. Today we're talking about segments. Totally different idea than the last couple of lessons that we've done. So we're talking about segments both inside and outside the circle. Our first scenario is segments of chords theorem. So we have two chords that intersect, kind of forming that X that we've been talking about. To find any of these sections or segments, here's our formula. So part of the segment times part of the segment equals part of the segment times part of the segment. So AE times EB equals DE times EC. So here's probably the easiest way to look at it. Part times part equals part times part. Another scenario, this is two secants where they meet on the outside. We have had pictures like this dealing with angles. Today we're talking about segments or partial lengths. Here's our formula. Easiest way to remember it is part times whole and part times whole. Looking at my picture, we would do EA times EB and then EC times ED. Be really careful with this because the biggest mistake you're going to make is if they tell you that this is 2 and this is 4, you have to add those together to find the whole length. It's not a hard idea, but when you're multiplying for your formula, it's easy to make mistakes. So again, it's part times the whole, part times the whole. And if this makes sense, this is just a little bit different. So this is a secant and a tangent. This side, this secant, same as what we just did a minute ago. The part times the whole. So EC times ED is one part of it. And this only has one segment, so it should make sense to multiply it by itself. So according to our formula, we take EA, the tangent part, and square it, multiply it by itself, and then it's part times the whole. So again, be really careful finding that entire length that you don't make a mistake on it. Let's look at some examples. So the first example deals with the first theorem that we talked about. We're going to do one segment times the other segment of one chord, and then partial segment times the partial segment of the other chord. So when we set this up, it looks like this. 6 times x plus 4 equals 12 times x. These parentheses do have to be there because it tells you that this segment here that has a length of 6 times this segment, it's not just 6 times x, it's 6 times x plus 4. So that's a distributive kind of problem. So when we distribute 6x plus 24 equals 12x, subtract the 6x, so x is 4. And it does ask us to find x. Always be careful that you're answering the question. So the next one, very similar. So for this one, same idea. This segment times this segment equals this segment times this segment. So setting that up first, we have x times 2x minus 1. And then the opposite direction, x plus 2 times 2x minus 4. Over here, we're going to distribute. Be really careful with exponents. Remember, you kind of want to do this in two separate steps. When we multiply the numbers, we get 2. When we multiply x times x, we get x squared. Be really careful. Common mistakes there, all kinds of things that you guys can do. X times negative 1 is minus x. Over here, we're going to do our FOIL. Anybody feel like foiling for me? FOIL for me first. What do I get here?
3x.
Be careful. 2 times 1 gives me, and then x times x gives me x squared. That's common mistakes. So x times 2x gives me 2x squared. Remember, you have to multiply the coefficients, then multiply the variables. Okay, so that's our first, our outers. What's negative 4 times x? Negative 4x. That was our outer. Inner was 2 times 2x plus 4x. And the last, negative 4 times 2, negative 8. So again, first, outer, inner, and last. So the next thing I'm going to do is kind of clean this up. I see 2 that are cancel each other out. Negative 4x plus 4x goes away. So I'm going to rewrite it without that. So at this point, I suspect I might be factoring, so I want to get everything on one side. when I do that, whether I move this 2x by subtracting and putting it over here, or if I subtract this 2x squared and put it over here, either way they're going to cancel each other out. So these are gone. I have left negative x equals negative 8. Divide both sides by negative 1 and x is 8. And they ask us to find x, which means we're good. Look at the next one. This one is the second theorem that we talked about, where we're going to do outside part times the whole equals outside part times the whole. So let me make some room here. So one direction, let's do this one first. The outside part is 2. The entire length is 10 plus 2 gives me 12. This direction, the outside part is 3. The entire length is x plus 3. Please don't say that's 3x. You're adding. That goes back to chapter 1 stuff, segment addition postulate. So this is x plus 3. So again, part times whole, part times whole. This side we get 24. This side we get 3x plus 9. Subtract 9 and divide by 3. We get x is 5, and that's what we're asked to find. Look at the next one. This is a similar kind of problem, but they're asking you to find RT and TV. These two are set up in the same way. The only difference is we're going to find x, and then we're going to plug it back in to actually find that length. I'm going to actually do this one on the TV to give me a lot of room to set this up. So the same thing, outside part times the whole, outside part times the whole. So let's set this up first. So using TR, the outside part is 27. The entire length is 27 plus x. The top part, the outside part is 21. The entire length is 2x plus 29. You see where that came from when you look at the picture? Okay, help me out with Desmos. Let's distribute 27 times 27. What does that give me? 729. Is that what you said? And then distributing, we have plus 27x. On the right-hand side, we have to distribute that 21. 21 times 2x gives me 42x. And I need 21 times 29. 609? Okay, I'm going to move my 27x over by subtracting. So what's 42 minus 27? What's that give me? So again, I moved my 27x by subtracting. Let's move this 609 over. What's 729 minus 609? What's that give me? Divide by 15, what does that give me? Should be 8, right? Okay, now we found what x was. We're asked to find what RT and TV is. So RT is made up of 27 plus x. We now know what x is, so what's RT? 35. And we're asked to find TV. TV, we already combined them, and we said that was 2x plus 29. We now know what x is. So what's 2 times 8 plus 29? What's that give me?
45.
Yeah, that's right.
Yeah.
Okay, let's keep going. These last two problems are the last theorem. It's our secant and our segment. So take a look at the first one with me. I'm going to do this one on the board. I think it's easier. I can spread out a little bit more. So this one is a tangent and a secant. And our formula, our theorem, tells us to take that tangent, multiply it by itself, and put that equal to the outside part times the whole. So let's set it up first. So the tangent squared equals the outside part is x. The entire length is x plus 42. A little bit different setup, but if the last two problems make sense, this should make sense too. Okay, 20 squared, what does that give me? 400. And then when I distribute, x times x gives me x squared. X times 42 gives me plus 42x. At this point, I suspect I might have to factor, so I'm going to put everything on one side. Subtracting that 400, moving it to the other side. So at this point, you have a couple of choices. Going back to your algebra skills, when you're solving and figuring out where it crosses the x-axis, that's your solutions. That means that you can either look at a graph, you can factor it, you can also use the quadratic formula. Because these are bigger numbers, you have more options when you factor, which could take you a little bit longer. So in this case, we're going to review the quadratic formula. And I do have it on the board over there. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Where does a, b, and c come from?
The triangle.
No.
No.
Yeah, I know what you're thinking. You're thinking a Pythagorean theorem. That's not what we're talking about here. Where's a, b, and c come from?
I feel like the first, second, third.
Does this look similar to that? Okay, so what I have in that particular equation, a is 1, b is 42, and c is negative 400. By using the quadratic formula, it will work for anything. There are some equations that are not factorable. So you can sit there and try to factor this and hit a dead end and realize it's not factorable. This will work for anything. So it's a good thing to have because sometimes you're going to have to use it. You won't have a choice. Okay, we got it. Okay, so let's use, scared me there. Let's use this and put it into this. So negative b is 42. So negative 42 plus or minus the square root of b squared. Yeah, let's try that again. Minus 4ac all over 2a. All I did was plug it in. I always put everything in there, even though it seems pretty easy. I don't simplify until I get to the next step. I'm always nervous that I'm going to lose something, so I always put everything in there as my first step. So now we can start simplifying. Inside this radical, let's bring everything down except for what's in the radical. What's 42 squared? What does that give me? What's 42 squared? Nobody has it for me?
Can you just get rid of the exponent because it's square root?
No, it's a good question. Because this subtraction is here, you can't do that. If it was just this, absolutely, you can get rid of the 2 and the square, they cancel each other out. But because there's a subtraction in there, we can't do that. So 42 squared, I'll help you guys out, is 1,764. Over here, we're subtracting, but we're saying negative 4 times 1 times negative 400, which gives me plus 1,600. 2 times 1, of course, gives me 2. Next thing I'm going to do, I'm still working under that radical to simplify. When I add these two things together, what do I get? 1,764 and 1,600. Say that again. At this point, I'm going to square root. I'm still trying to simplify that part. So when I square root 3,364, I get 58. So at this point, I'm going to do two problems. Let me write it up here. I'm going to do negative 42 plus 58 divided by 2. And I'm going to do negative 48 or 42 minus 58 divided by 2. That's what that plus or minus means. You have two separate answers. Remember, when you're factoring, you typically get two separate answers. When you're looking at the graph, you'll see two separate places where it crosses the x-axis. So what are my two answers that I get here? Negative 50 is 1. I believe it's this one that's negative 50. And what's this one? It is. Do both of these answers work in this scenario? If I define x as being 8, is that okay? Absolutely. Is it okay for this length to be negative 50? No. So I do want to see this on your work. Don't just assume. So show me that you got 50 and then cross it out and say that I know that that doesn't work. Okay, moving on to our last problem. Similar to this one, we're going to do tangent squared equals outside part times the whole. So when we set this up, x squared equals outside part times the whole. When I add these two things together, the 2's cancel out, and I just get 2x. Again, I'm adding those two segments together. So when I distribute, I get 2x squared minus 4x. I'm going to bring this x squared over by subtracting. So I get x squared minus 4x. In this case, this is a factoring kind of problem, but anytime you're factoring, you always want to look for something they have in common. What do these two terms have in common? An x. So I'm going to factor out an x, almost like setting up a distributive problem. So I'm going to factor out an x, and I have x minus 4 left. Do you guys see how if I were to distribute this to this, I would get this? So I was kind of setting up a distributive kind of problem. Now I have two terms. I'm going to set each of these terms equal to each other, or I'm sorry, equal to 0, and solve. I have one answer. My other answer is 4. Does 0 work? No, because this can't be 0, and this can't be negative 2, so this one gets thrown out. Does 4 work? 4 is good here, 4 is good here, 4 is good here. So this is our solution. This one you could have used the quadratic formula for, but being that I have enough experience doing this, I could see that these were smaller numbers and very doable. There's nothing wrong with using the quadratic formula every time. Nothing wrong with that. Okay.